So the first speaker is David Saylor, and he will talk about on the front lines of extreme heat, experimenting with innovative strategies and technologies for cooling the hottest US cities. Please, David.
All right. Well, thank you. Thank you, everyone, for making it this morning. So yesterday morning, we started off with a bit of a discussion on global climate and climate change at global to regional scales. Today, I'm going to start us off by talking about local climates, urban climates, and in particular, what cities are doing to try to address them, as really the local climate is the driver for the built environment. So in the US, we have a very significant portion of our population living in what we call the Sunbelt of the country. So it's about half of the US population is in that southern third of the country. And in fact, it's the fastest growing part of our country. So 75% of population growth over the last decade has been in the Sunbelt. The city of Phoenix, which is where I'm from, is the fastest growing large metropolitan area in the country. And a lot of the reason for this is a combination of things like cost of living. It tends to be cheaper in the South. Tax structures in a couple of states in particular, Florida, Texas, Arizona, make it very attractive for families and businesses. And the climate, somewhat ironically, the climate is a driver for bringing people there because at least half of the year it's absolutely gorgeous. It's the other half of the year that we need to talk about this morning. And the final point that's I think kind of an interesting add-on here is that COVID really sort of tipped the scales. There was a growing move to work from home across our country, I think in many parts of the world. And COVID just accelerated that. So now it doesn't really matter where your job is as much. There's a lot more flexibility to live where you want. And as a result, these areas are likely to see continued growth. They're also some of the hottest parts of the country and the most water stressed. And this is for a handful of reasons. Primarily, we think of the urban heat island effect as a driver of local warming. But then also global climate change, of course. And so what I've plotted here is simply the minimum nighttime temperatures in Phoenix for the last 50 or 60 years. And what you see is that the minimum temperatures have risen about 5 degrees Celsius. So that's how much you're able to cool off at night. It's now 5 degrees Celsius warmer than it was 50 years ago. And interestingly, of course, during the day, if you look at daytime averages or if you look at daytime maxima, they too have increased, but not nearly as much, maybe 1 to 2 degrees Celsius. So there's a lot of warming, particularly during the night. And there was a paper almost a decade ago now that made an argument based on atmospheric modeling of regions across the country that demonstrated that anticipated global climate change is on the order of the same magnitude as the anticipated urban heat island warming associated with the expansion that we're expecting to see in these parts of the country. So it's worth noting that a lot of the climate change that we're dealing with locally is locally manageable. And so that's what a lot of my focus today is going to be on. Now, the reason why we care about extreme heat across these cities is for a number of reasons. Obviously, thermal comfort is one of them. In the extreme, heat-related morbidity and mortality are of growing concern. And here what you see plotted is just in Maricopa County, which has a very strong health department that gathers very good data. They've tracked heat-related deaths over the past decade or so. And what you see is a very steady increase in the number of deaths per year. So the population of the Phoenix metro area of Maricopa County is on the order of 4 million people. Last year, we had 339 deaths that were directly attributable to extreme heat. So that, you might think, is an argument for, wow, we're going to see increased deaths going forward. But at the same time, we have to recognize that the links between heat and mortality or morbidity are not simple. So here I plotted just one metric of the thermal conditions across the city. This is just cooling degree days. You can do it in terms of maximum temperatures or average temperatures. But from the period of 2014 to 2021, what we see is that there's clearly a disconnect. Sometimes you'll see a decreasing trend of temperatures for several years, but flat or increasing deaths. Sometimes you'll see it just the opposite, very, very significant decrease with an increase in deaths. So it's clearly not just the heat. Another thing that we need to recognize is that not all these deaths are happening indoors. I think there's this perception that that's the case. And in fact, in the Phoenix metro area, it used to be about half of the deaths were attributable to indoor exposure. Now it's down to about a quarter of the deaths. And part of that is due to increased homelessness. Part of that's due to increased prevalence of air conditioning in buildings and better air conditioning systems in general. But what we see is about a quarter of the deaths are in an indoor setting. So these factors combined make us recognize that we need to think about solutions that address not just the indoor, but also the outdoor exposures, and that we also consider what are the other causal factors that are contributing to our rising death rates. And I started my research career back when I was a grad student, looking at how can we cool cities. I focus on the city of Los Angeles, California, and back then our focus was, well, what could we do to cool the entire city? So we would in our models plant 1 million trees uniformly distributed across the city and so forth. But increasingly, we're recognizing that if we really want to have a significant impact, maybe we want to target our solutions. And so we can achieve greater impact by targeting our mitigation, recognizing that the health risks are really at the intersection of the hazards. So it can be heat hazards, air pollution hazards, exposure, and then, of course, vulnerability. So what are our most sensitive populations? It's typically the elderly, it's typically the very poor that have low adaptive capacity and so forth. So this is just an example from some work we've done in Los Angeles where we've asked the question, where should we focus limited resources to try to cool the city to have the most benefit? So you can look at census data and you can identify where some of the most vulnerable populations live. So the elderly, the poor, you do an intersection of elderly and poor, and you get a much smaller segment to look at. You then add in where is it the hottest, and certainly, LA, California, being coastal, you don't really get extreme heat till you get a little further inland. So you can identify much smaller parts of the city where you can really have a huge impact with your limited resources. So a lot of our work lately has really focused on that approach. And this brings me to another opportunity that we've identified in Phoenix, which is that not everyone is uniformly vulnerable as we would expect. But if you look at certain housing types, so those who live in mobile homes or in manufactured housing, they're on the order of 5 times more likely to die of extreme heat than individuals living in any other kind of housing. And then I know, for example, say in the European heat wave of 2003, it was primarily the elderly living on top floors of apartment buildings. In our case, it's much more these low income, poorly constructed buildings that are most at risk. The other thing that we focus on a lot in my group is the passive survivability of buildings and the recognition that power outages are a reality, and actually our electric grid is incredibly vulnerable. And if you just look at the power outages that we've had over, say, the past 15 years, this is a little bit dated, but if you limit yourself to what we consider major power outages, so power outages affecting at least 100,000 customers, that's more than 100,000 people, for at least 10 hours. We had over 512. We had 525 such outages in the US alone during that period. Now, many of these are caused by events that are not coincident with extreme heat or extreme cold, but many of them are. And you can just imagine what would happen in a city like Phoenix, where the saturation of the air conditioning market is 99%. So 99% of the homes have air conditioning of some form. If you suddenly had a power outage in a city that relies on air conditioning to survive, we would have many, an order of magnitude more deaths than we'd have in a typical year. So that brings me to our approach for working with local governments. So specifically, we see our university as being really a research partner or the research arm for local and regional governments. And we recognize that there's a need to have the university play a role in informing government of the pros and cons of different technologies, life cycle analyses, and actual performance metrics, because industry oftentimes will try to sell things to the city governments that are not necessarily vetted. And so our goal is to be that independent agent working with government and stakeholders to identify solutions that work the best. So what I'm going to focus on for the rest of my time is just some example projects that we've been working on in the Phoenix metro area with local government. So there are 22 local cities that make up the Phoenix metro area. And so we've been working with a number of them, 3 of the largest cities in particular, to identify solutions and to try to see if we can really deploy solutions at scale. So the first example I'm going to give you is a really interesting project that started about 5 years ago when I shortly after I arrived at Arizona State, and the city had just received a redevelopment grant from the Housing and Urban Development Department from the US government, and it was going to allow them to redesign a very old development that was poorly constructed. It was costing them $1 million a year to maintain. And so they came up with a plan to raise the entire area and replace 500 low-income social housing units with 1,000 mixed units of about half low income. And so they did this in a strategic way where they first built out on some new land, and then they started knocking down old buildings and moving tenants as necessary. But what was really interesting about this project was that they involved our university early on to try to help them develop a plan for better design of the neighborhood. So how do we design the courtyards? How do we design the buildings and the layout of the buildings? How do we reconfigure what was just a large, relatively unused park at the northern end of the community to create this linear park that gave more access for the residents? And so we designed really an experiment that included everything from physical measurements. We have about 9 weather stations distributed throughout the area that are gathering data continuously. We did walking interviews with residents. We did surveys of residents. And then we informed our models with these observations to try to understand if you make a variation on the design, what does that do to the outdoor thermal environment? And so that is a really good example of sort of university community government engagement around providing design guidance. That project is still in the construction phase, so we don't have any results to share from it. Another thing that we're doing with the city in Phoenix is, again, recognizing that it's probably not very cost effective, especially in a city like Phoenix that's water stressed, to plant, say, 1 million trees, right? But the city has this concept of simply creating a network of cool corridors in some of the most vulnerable communities that facilitates movement of residents between their homes, their employment, and their places to play and be educated. So these are typically, like I just visited one last week that was designed to go between a school and the local library. So, this is a nice idea. In reality, trees, especially in the desert, take quite a long time to grow. And so you typically plant trees that are not very large, and they take quite some time to really cast the shade. But it's a long-term strategy, and ASU, my university, is part of helping to identify or prioritize areas where these cool corridors should go, and then evaluate them in terms of their performance, in terms of the mean radiant temperature environment that they provide for pedestrians. And recognizing that trees are a challenging commodity in a desert climate, even though we do use desert-adapted natural trees from the environment, we want to supplement this concept with shade structures that are more artificial in nature. And so we've been exploring a couple of technologies related to providing shade that is not just your typical shade, but that uses surfaces that have extremely high solar reflectance and extremely high thermal emittance that allows you to create shade surfaces that are actually cooler than other surfaces in the environment. They radiate less heat down to the pedestrians underneath, and as a result, you will feel more comfortable. So we have tested this out in a partnership with local government. In this case, it was City of Tempe with their transportation program and an industry that provided a cooling film that has these radiative properties that we desire. And we modified bus shelters, and we monitored. We had fixed monitors on the shelters themselves to look at surface temperatures, air temperatures, and we did periodic measurements of mean radiant environments for the bus shelter users. And what we found, and I'm going to go through this relatively quickly because I know we started late. But what we found is the orange dots here are the conventional bus shelters, so just the standard old bus shelters. The red line is sort of a running average. So follow the red line for conventional, and then this darker line down here is the surface temperature of the shelter for the radiative cooling shelters that we tested. And what you see is this is actually a difference of temperatures from the surface of the air. So 0 means the surface was exactly the same temperature as the air. And what we see, lo and behold, is that your typical bus shelters are on the order of 5 degrees Celsius hotter than air, averaged over the day, whereas the radiative cooling shelters were on the order of a degree cooler than the air. And so if you can create surfaces that are consistently cooler than the air that surrounds them, then as the air flows over the surface picks up heat. The surface then radiates that heat through the long wave radiative window, mostly out to space. And so it's a mechanism to provide both that local thermal comfort, but also to provide local cooling to the airshed. And so this just shows that if you do if you look at the top and bottom surfaces of one of these shelters, on average, we get a reduction of about 150 watts per square meter of heat convected into the airshed. So it's an effective mechanism for cooling the airshed. Another project that we've done with the city of Phoenix is looking at paving. So paving in a typical city in the US, there are lots of surface parking lots, lots of paving. It's 20 to 25% of the surface area of most cities. And so the question is, can we use what's known as cool paving, again, more solar reflective paving than your standard dark asphalt, to actually absorb less of the solar energy during the day, so it then releases less heat into the airshed at night. Because as you'll recall, that's our real big challenge in Phoenix, is that we've been heating up so much in the nighttime hours, we need to make sure we're storing less heat during the day. So this study looked at 8 neighborhoods in city Phoenix. It modified 58 kilometers of residential roads that were already slated for resurfacing. So, your typical road, at least in Phoenix, lasts about 5 to 7 years before it starts to develop cracks, and you typically seal coat it, usually with a very dark surface. Here, what we're doing is we're saying, well, what if you seal coated it with a lighter product? So we used what's known as a cool seal product instead of the conventional dark seal. And then ASU was monitoring subsurface temperatures, surface temperatures, air temperatures in the neighborhoods, and we were sampling the pavement spectral reflectance over time to see how it degrades. And so this is just an aerial shot of a typical neighborhood. There's no cool paving in here. This is just an aged street. So dark asphalt lightens over time. And then here they had recently done a dark seal coat. So this is just the normal difference that you see. And if you look at the differences in temperatures between these two surfaces, you see that as asphalt ages, you get a benefit. It's more reflective, and the surface temperature is reduced by about 5 degrees Celsius on a pretty hot summer day. Now, if you look at what happens when you replace, instead of replacing the aged asphalt with dark, you replace the aged asphalt with light, the cool seal, we get about another 7.5 degree C cooling. And so it stands to reason that you would see about a 12 degrees Celsius difference in surface temperatures if you do cool seal instead of the black seal. And what we did do also was we ran a number of measurement campaigns where we drove instruments and we pulled instruments through the neighborhoods pre-sunrise, early morning, noon, around sunset, and then in the evening hours. And we looked at identifying temperature differences across a neighborhood that had entirely cool seal. So this image is when they were halfway done with a road. So we did a neighborhood that was entirely cool sealed and then a neighborhood that was just conventional aged asphalt. And we found on the order of a 0.5 degree cooling of the air shed. So that's some of the work that we've done with the various city governments trying to cool outdoor ambient air. Now I want to just spend a little time, and I don't have much time, so I'm only going to talk about really one building-focused solution, sort of the reflective properties of building facades. We've also done a lot of work with thermal mass and phase change materials, which I can talk about later if we have time. So, oftentimes in cities you get very dark rooftops, and if you simply replace them with lighter rooftops, you get dual benefits, right? So you get cooler surfaces, so you're convecting less heat into the air in the city, but you're also conducting less heat into the building, so you have better thermal resilience, you have better thermal comfort in general, and less energy use if you have air conditioning. And you can go to the extreme. These are some panels that are actually the high solar reflectance, high thermal emittance panels. But if you look at, this is a satellite view of a shopping mall in Phoenix, and you can see it's got this one happens to have a dark roof. The parking lot is a little bit darker. This is a large hardware store with a white roof, and then a bunch of buildings with white roofs also. What's interesting in the thermal is that, of course, the shopping mall is extremely dark, extremely hot, hotter than the pavement, which is even darker. And that's because the roof is very well insulated, so it's storing most of that heat near the surface, convecting into the air shed. Same thing with this hardware store. It's as white as these residential buildings, but it's actually a little bit hotter because it's better insulated. So there's this interesting thermal connectivity between the building facade and the indoor environment. As you insulate the buildings better, the building surface is more important for the ambient environment. As you have less insulated buildings, it's more important for the interior environment. So you can still go around Phoenix today. This is a helicopter shot of some buildings not too far from my neighborhood, just a couple of miles away, where you see dark roofs. And of course, those dark roofs are extremely hot. They're contributing to heating the neighborhood, as well as to increasing the air conditioning bills for that house. So one thing that we've done, this is not a demonstration project, but just a modeling project to help inform the work that we've been working on, is we looked at the question of if you replace a conventional roof, so we define conventional as a 20% reflective roof, 0.9 emissivity, which is fairly typical, with what's typically considered a cool roof or a white roof, so solar reflectance of 70%, also emissivity of 90%, or you replace it with a passive daytime radiative cooling roof with a much higher solar reflectance, much higher thermal emittance. How does that affect we did both building roof surface temperatures, convection into the environment, but also the air conditioning energies for buildings. We did this across 8 climates, including 8 cities, including 6 that are in the Sunbelt. And lo and behold, what you find is this is again a plot of surface temperature minus air temperature. So this is surface air temperature differences. And so 0 means at the same temperature. And if you have a conventional darker roof, you'll oftentimes have the surface that's 20, 30, or even 40 degrees Celsius hotter than the air. And at night, of course, it subcools. A white roof still gets 10 to 20 degrees Celsius hotter than the air. A super cool or passive radiative cooling roof actually never exceeds the air temperature. So it's always taking heat out of the air, radiating it to space. And you can look at the results in terms of energy use. Here I only have, in terms of diurnal sensible fluxes, again, the conventional roof is this dark area. This is summer over here for a retail building. And you typically have a sensible heat flux that peaks on the order of 300 watts per square meter. Put in a white roof, it peaks around 100 watts per square meter. Put in a passive radiative cooling roof, and it's sub-zero. So it's less than 0 watts per square meter, meaning it's taking heat out of the air. So I just want to close with a final thought here. So one thing that we've been working on is, I've done a lot of work over my career on what's known as anthropogenic waste heat. So how much heat we're putting in the environment as a result of our energy consumption. And we've started thinking about this differently lately. Consider this lone building that we've built on this plot of land. The waste heat that this building puts in the environment, typically we'd think of as being, well, the heat generated or rejected from the air conditioning system, or maybe we would think of it in terms of the total energy use of the building. But what we're doing now is we're thinking about it in terms of, well, in the absence of the building, we would have had convection into the air from the surface of the ground anyway. What happens when you add a lone building over that land is you have convection off the roof surface, the wall surface, and waste heat rejected from the air conditioning. And so this dashed line simply shows you only the ground heat flux for a particular case. This is, again, is in Phoenix. So it peaks only around 50 watts per square meter here, average over the summer months. And the air conditioning rejection is a little bit less than that from a typical air conditioning system. And the convection off the wall is not a huge amount, but the convection off the roof surface is twice as large as the waste heat rejected from the air conditioner. So we're putting a lot more heat into the environment because of conventional, just sensible heat flux convection off of rooftops than we are from HVAC units. So the question here in red is, can we get net negative heat release from buildings? So can we have building projects that actually cool the environment relative to the land they replaced? So this is kind of like a net negative carbon concept, but it's applied to heating our environment instead. And the answer is yes. So very, very shortly, these are just a number of different ways that you can get below zero. So this is relative to sensible heat flux from the land. Yes, in fact, we can across all months, and what's most important here is really the summer months, we can get below zero. We can have a building that is a net negative heat generator for the environment. So as we think about building out our cities, urbanization does not necessarily need to go hand in hand with increasing the urban heat island effect. So that's all. I'll just close on that.
Because you are good on time, I think we will take one or two questions just now.
I like being accused of being good on time.
I have a first one. You said for the last slide, you also have effective air conditioning. So it's really the air conditioning that are removing the heat from outside.
So
you said the buildings where you could make them negative, so they could remove heat. They had a very effective air conditioner.
Yeah. Well, so they had we looked at 3 different SEER levels for air conditioning. One is equivalent to what I just installed in my house, and then one was what was higher. So your typical newer air conditioning units give you that COP. So you with existing equipment and just slightly higher solar reflectances of rooftop and wall surfaces, you can get sub-zero. So it's not all of the air conditioning. Okay. And then of course those more efficient units, they're just rejecting less heat. So of course they're rejecting heat, but any heat they take out of the environment, they reject back into the environment. Well, any heat they take out of the indoor environment, they reject plus their inefficiencies, right? So
okay.
So that's accounted for.
And then we have in the chat, can you read it?
So thanks for the overview. New federal climate legislation will include substantial funding for low-income weatherization. What approach would you recommend to optimize climate adaptation and resilience for those homes? From Tom Phillips. Okay, so one thing we've done when we look at weatherization is it's largely focused on heating climates where you need to weatherize to keep the building warm inside. What we find is that in certain climates, in the cold climates, the weatherization actually makes the buildings more resilient to, say, power loss, air conditioning failure. In hotter climates, it actually makes them less resilient, and largely because it does not allow. I'm sorry, I think I had that backwards. It doesn't allow for the free cooling at night as well. So you have to be more cautious about your operating windows. And in a city like Phoenix, in the summer, it'll often be like the minimum temperatures will dip down to 32 Celsius for a few hours from like 3 in the morning to 6 in the morning. So you really don't have the ability, unless you want to wake up 3 in the morning and open your windows, or you have an actuator system. It's difficult to take advantage of free cooling in some climates.
Okay, thank you. We will go to the next speaker.